So this work was done by myself and my co-authors listed there. Was mostly to try and compare IOURING versus TCP devmem, and back in Santa Clara we did some of this work, but there were some features missing from both devmem and IOURING. So again, it's just to investigate these two. Our major goal was just to try and understand the performance characteristics and interfaces. How would someone write an app for this thing? And when we did, the last time we did performance measurements, we had access only to 100 gig link. Everybody could do 100 gig. Then the only differentiation became how much CPU is each one utilizing. So for this reason, this time around, we were able to get a fix from Intel, which allowed us to do 200 gigs on a single port on the same NIC. Okay, so in addition, around December, transmit side devmem was released, zero copy transmit, and since Santa Clara as well, IOURING zero copy receive showed up. So it was good motivation to submit something else, something new to the conference. Okay, so for those who are not familiar with zero copy, is my mouse showing up there? Yeah, okay. I'm not going to spend too much time on this. Who is not familiar with how zero copy works with header split? One. Okay, Christy, no. Okay, so what you have is you configure your NIC to do a header split. The packet comes in, and you memory map using the binding that was added a while back. You map your user memory, for example, to your payload memory. And if I was to draw this without zero copy, all these would be red implying that, trying my best to abstract here, meaning kernel memory, but in this case, we basically have the blue memory, which is user space, mapped to the receive payload and the transmit payload as well. Okay, summary. And you could actually take accelerator as example. A GPU is the most common. Map that memory to the receive queue on the receive and on the transmit as well. Okay, I'm not going to spend too much time because I have a lot of other slides I have to run with, but essentially, for those who raise their hands, what happens when a packet comes in, the header payload, the header splits the header. It does a parsing, matches some header tuples, splits the header from the payload, queues the payload on the blue and the header on the red, and the kernel TCP will process this, and a receive message running on user space as such here would get receive message notifications with memory offsets, etc., etc. Okay, I'm not going to spend too much time, like I said. Let me describe the setup target and traffic. So, to quote David Ahen, where's David? Yeah. So back when we presented our results with the many flows in Santa Clara, he said, you know, if you really want to do benchmarking, you have to tell us how much you can do with one flow. So our ultimate test is to try to fill a pipe with whatever hex, gigabits X is variable with just a single flow. So we're doing an asymmetric test. Basically, there's a sender who sends the payloads, the receiver receives them, really does nothing with them. Our MTU was large enough to cover the appropriate MSS, which is 4108, it's 4096 payload and 12 bytes for TCP options. It's IPv4. We run very long flows, mostly up to 100 seconds. And we try to write as much as 64 megabyte, send and receive, okay? I'm going to skim through this as well very fast, but if you want, you can slow me down by raising a hand or whatever. The motherboard is not very sophisticated. Well, it is sophisticated. But it's not a new one. There's only a single core in there with, I think only Intel builds these motherboards. It's called the Ruby Pass. It's got a single Sapphire Rapids, which is known as the Eagle Stream platform, I believe is the marketing name, 48 cores with ton of hyper-threading. So we've got 128 gigs of RAM, and we wrote our own homebrewed application. I'll add, it's written in Rust. And we bound one of the CPUs, was bound to soft RQ, essentially to the interrupt, with only one queue pair being used, and the other was bound to the application. So all the traffic lands on single CPU. On Q0, it goes up, the app processes on another CPU. That was our original goal. We have two Intel IPU 2100s. Like I said earlier, and we're using the upstream driver, the IDPF. Single cable, it's a 200 gig. The NIC is placed on a PCI 4x16, so we should be able to do 200 gig given that capacity. Header split, the NIC can do header splits, scatter gather, checksum, TSO, hardware GRO, that was an interesting feature. And we set the transmit and receive ring to 4096. These are some of the other settings on the receiver and the sender. Kernel 614 RC1 with some extra patches on top. Some simplistic hooks for page pull so we can do devmem. There was an issue with the hardware GRO that was fixed by Sridhar. We enabled big TCP. You have to basically patch the kernel to change the size to 131K, and then you configure the kernel config max XAB frags to 45, which is a nice improvement compared to when we last showed up in Santa Clara, where you actually have to go and hack the code. We got a lot of help from Pavel with IOURING, and we used his V13. We pulled it from GitHub. Mina was extremely helpful as well. We used his version from December 2024 because that's what, when we first saw that, that's when we decided to do these tests with some bug fixes, which I'll mention after. There were other patches that followed up in January, but the API had changed. We tried to use them. We found a bug. Then we said, okay, let's just go back. We already built the infra for the tests. Okay, so we're interested in three metrics. Number one is throughput, power consumption, CPU, and we compute our results based on this three metric. We have a little box that measures power that's measuring the whole box as a black box. And our test durations was about 100 seconds at 64 megabyte messages. You end up sending like 1 terabyte across the link. So over 100 seconds, even if there's glitches, they kind of even out. We repeated 5 times. We throw some of the results, we pick something in the middle. I don't think it was absolutely necessary, but the first one definitely is good reasons to throw out. Start in governor mode. As you run in the 100 seconds, the power goes up. So we do ramp up in the power, okay? You can also bring me back to this afterwards. Okay, so it looked good. We picked our test cases. We didn't want to do too many tests. So receiver side is a permutation of, we have software GRO versus hardware GRO versus big TCP versus no big TCP on both sender and receiver. Our baseline test is there is no zero copy. It's just classical socket application with send and receive. And then we did zero copy with devmem and IOURING. And then on the sender side, we varied between big TCP and no big TCP with baseline. And for zero copy transmit, devmem versus IOURING. So any questions? All right, so who knows what, who doesn't know what here be dragons means? Everybody knows? Shriyit knows. Does anybody else know what here be dragons means? Okay, since I have time, I'll explain. So back in the day, pre-medieval days, when people drew maps and they had no idea what you'll find on some place, they'll put dragons on the map. And that would mean that If you go there, you may meet dragons, right? So, and it will say, I think the writing will go, here be dragons. Right? So you'll find some dragons on the way there. And we did find some dragons, okay? So some bugs were fixed. There was one for the TX where the global binding for TX iteration on the buffers was not working. Fixed that, took us a while. There was a patch that made it in from Sami, I think, at Google, that we had to undo some things. We have not pushed that patch upstream. I think privately sent it to Sami, but I never heard back from him. And the IDPF driver is lacking a few things, one being the page pool stats, which we added. It was a quick hack. It turned out it didn't help that much. Okay, IOURING. So let me go over, the IOURING had less issues. It's still cheating on IO weight accounting. Pavel has a patch, but we never tested it. So if you run a lot of CPUs, you'll see that it's sitting there waiting for IO weight a lot. And in fact, this could account up to, let's say, 35%, right? If you have 2 CPUs. And on the transmit side, it's even worse because you see up to 87%. Again, Pavel did provide us a patch, but we never used it in this test. I wasn't sure if it's because, I think it wasn't applying cleanly. Pavel can confirm that or not. Is Pavel here? Thank you. Okay, so in the way, so it showed like it was utilizing less power, less CPU, but the power was compatible to what we were expecting. So that's what I wouldn't call it cheating. It's just a technique they're using. And if you look before Pavel's patch on the left side, and then after the patch, you'll see that the power states change. So that was the major qualm, and it's not a big one with the IOURING. Okay, so now we're going to devmem, because the rest of the things I'm going to describe is just mostly about devmem. Okay, so the first thing you need to get right is the provisioning of the page pool, which is, this is a feedback control system, right? So you have to fill the tank, right? Traffic is coming in, and okay, I'm just gonna, where's my mouse cursor? Okay, thanks. Okay, so incoming traffic, as you flash from the page pool, you need to make sure that this flows cleanly, that you have enough buffers in there to flash whatever is coming in, as well as in flight, it's filling up. Okay, so classical feedback control system, everybody's familiar. It's the easiest example I could find. So next, we basically, the first thing we did is we found that the path profile was showing, damn it. My cursor not showing up at all. Oh, okay. Anyway, what you see on the top, which says bad, that's before, if you don't provision your page pool correctly, you're going to get a lot of trashing. Then you provision it correctly and it looks better. You see the TCP receive DMA message receive DMA buff at the top. Now you know you got it right, but look at the previous perf and it does not look as good. Okay, so we ended up allocating 64 megabytes of UDMA buff for the page pool. We also observed that if we made a smaller receive message, let's say around 512K, the performance was not as good. So with 64 megabytes of UDMA buff on the page pool, our performance improved by 30%. Okay, so that's the one thing you need to know. It requires management. IOURING will, this is, you basically have to go and look and see, oh, why is my performance bad? You dig a little bit deeper, and then you know it's because of the page pool. And IOURING has a much nicer feature, which is you get events, actually. If you if you are not keeping up, let's say, for example, with the reception, you will get this IOURING. So you set up the IOURING with feature not drop, and you get notifications, right? So so that will be a trigger for you to go and reconfigure things. All right, so run the fast test. Throughput, just looked at throughput, nothing else. Everything looked sane. This is 2 CPUs again. The black is indicating hardware GRO versus no hardware GRO, okay? So baseline maybe is reasonable, it's about 83, 84 megabytes. Devmem did not, sorry, hardware GRO did not do much to help. Now you would be expecting hardware GRO to improve over no hardware GRO. That's the rational gut feeling. And that's true for everybody, except for devmem. So again, another dragon pops up on our journey to just run what we thought would be a 1 week's worth of effort. But what is impressive here is you can see, for example, IOURING, excuse me, with 2 CPUs is filling up the pipe almost 190 gig. You would probably, PCI 4 at X16 is getting closer to 200 gig. So you're probably dealing with PCI overhead at this point, right? The encapsulation overhead. So seeing this, knowing that a lot of the devmem inherited some of the techniques, not all, but some of the wisdom that was in message TX0 copy as well as in RX0 copy, Eric, we went and decided this was not part of our plan. Let's just go and run a transmitter with message 0 copy and receiver with what Eric had done. So Willem on one side, transmitting, Eric on the other side. And yeah, it's the behavior we expected, right? It's the hardware GRO was producing better results than no hardware GRO. And in fact, for hardware GRO, the performance was better than that. Right, now remember, we did not want to do this. We spent about a day or more figuring what the hell is going on. Did we misconfigure something? Did we write the app incorrectly? And so went and collected the CPU utilization. I just want you to pay attention to the devmem before, without hardware GRO. Blue means it's system calls. Red is around what the application is getting. The application is not doing much, really. It's just receiving the received message, counting a little bit, and letting go, basically recycling the buffer, okay? The software RQ is yellow. That's the software RQ CPU, and this is the syscall CPU where the app is running. Okay, so see, it's very overloaded with syscalls here. Then we turn on hardware GRO, and it's using a lot less CPU, but we're getting worse performance, okay? So now, if you look at message 0 copy, transmit and receive, it's behaving sanely. That's what we would expect. Okay, so we looked at power next time. So I'm ignoring the transmitter. I'm only looking at the receiver. Yes, power is as expected, using less power with hardware GRO, a lot more with no hardware GRO. And it's consistent across, except for here, this could be just a glitch. It's very small difference. Okay, so at this point, say let's go and run perf. Okay, we're looking at perf from both devmem and IOURING. Nothing really stands out, but looks, whatever syscall stuff in red, there all seems to be syscall and user space related. Okay, so say let's take a look at what syscalls do. And this is a feature that I think, David, you added this feature, right, on perf? Right, it gives us statistics of how this syscall utilization goes. If you take a look, you'll see that, okay, I'm not even going to use the cursor, you can read that. First of all, look at the IOURING. The syscall is very, very cheap. There's only one syscall. There's a wrappers around the syscall, but it eventually you enter IOURING enter. If you look at the average cost, 7 microseconds on average, right? On the worst case scenario, we're hitting like 450 microseconds. Now you look at devmem, very, very heavy in terms of syscall, receive message. In the 100 seconds, essentially, it's accumulating to about 68 seconds. It's just running receive message. On average, consuming about 112 microseconds. Setsock opt, which is used for recycling the buffers to the page pool. On average, about 43 microseconds, consuming about 22 of those microseconds out of the 100. So it's pretty close to 100 microseconds. Unfortunately, we run our devmem approach by using ePOL weight, but it's very, very cheap. So I don't think it added much to the overhead, right? The ioctl there, if you use UDMA buff, remember that you have to do a sync, start, sync, end to UDMA buff. So that's what that is, but it's extremely cheap. I mean, on average, you're spending about 343 microseconds. Okay. So it looked like perhaps this was a locking issue. Some of these syscalls are hiding the details that there's a lock underneath. So we put everything. We put the application and the software queue on the same CPU, and voila, devmem is now behaving the way we thought it should behave, right? It's lower for non-hardware GRO, and it's much higher for non-hardware GRO. So it got fixed by just moving everything in one CPU, which typically points to a lock somewhere that's being contended by two CPUs. Any comments, questions before I unravel this mystery? Nothing? Okay. So compare the two now, right? On the left-hand side, you have the two CPUs. And if you look at devmem, you have 118 when you do not have hardware GRO, and you have 111 when you have GRO, hardware GRO. You look on the right, now I turn on, I put everything on one CPU, which should be, you'll have less compute power, basically. And it's doing better for hardware GRO. It went from 111 to 131. There's an increment of 20 gigabits per second, right? IOURING is performing excellent. As you can see, 190, we denied a little bit of CPU. With hardware GRO, it went down to 183. Excellent performance still, even when you don't have hardware GRO, from 139 to 136. So if you look at the right-hand side, single flow, single CPU, app and software queue all running on the same CPU. That's what we get, right? At this point, we're only looking at throughput. Any questions? No comments? Okay. All right, so let's go and take a look at the path between what is it that made a difference when we put everything in one CPU. So we look at path for both hardware GRO and not hardware GRO, two CPUs versus one CPU. Nothing seems obvious, but if you look at the top consumers, they're still syscall/app related. So let's go and take a look again at the syscall costs of one CPU. Now, the setsock opt is now more expensive than the receive message on devmem. The cost on average is now actually went down to 159. Let me just jump to the two CPU versus one CPU there. If you look at the top, that's the two CPU scenario where we receive message was costing on average 112 microseconds. And with one CPU, on average is 159. Setsock opt went from 43 microseconds to about 159 on average. So setsock opt seems to be, I'm sorry, to 203 to 203. So that's an increment of about 4 times. Right, so that setsock opt started looking suspicious at this point. We dig again, and voila, there is the issue. It seems that there is IDPF libeth is the problem. We investigated a little bit. It's holding a lock for the page pool producer on the receive, on the header actually. It wasn't. This is not even payload. It's header locks, right? Okay, we were getting closer. So I call this the IDPF hardware GRO Dragon, right? The Intel driver creates 2 page pools, one for headers, one for payload. You don't know a priori if you're getting hardware GRO or just single buffers per header, each with a header. So they're symmetric, okay? Unfortunately, when you have hardware GRO, you're getting 1 header and X number of payloads. So for the sake of discussion, let's say we had 16, let's say we had 16 payloads with 1 header. Each payload is about 4K, given the way we set the MSS. It means that only the first header is relevant. Now, what libith rx recycle slow, which showed up in that perf output, will recycle. Now it goes, oh yeah, this is a dummy header. I don't need this page. Let me put it back on the header page pool. In the meantime, the packet is bubbling up the stack. And at some point, the app will consume that. So it has to be eventually, it propagates down, SKB release, and it's contending against incoming packets which have dummy headers. Right, so the lock is held for each page that's going to be recycled once. So you grab the producer lock, you put the page, you release the producer lock, and there is something coming from that has been consumed by user space, and there's something coming down from this wire, right? So that happened to be the root cause for the first issue. And the key was recognizing that sec.opt with 1 CPU went up. Unfortunately, we didn't have time, neither the inclination to fix this issue, but we tried to reach out to Intel. We didn't really get a response, but we're still reaching out to them. So one potential solution, I don't know how other drivers are doing it. Is this a page pool philosophy? Is this how things are done in page pool, or is it just the Intel driver, right? So one solution is maybe why not keep a single page and put multiple headers there and then use ref counts. I don't know if ref counts are more expensive than the scheme of recycling the 15-page payload. So my theory is, and I did not include here the shared info on the SKB, but you could fit a lot of headers in one page. Eric, any comment on that? Or okay, Mike there. So, Mike.
Of course, you know that I have some comments. First of all, when the TCP receive message do the consume SKB, normally this SKB is sent back to the CPU which allocated the SKB. So normally you shouldn't have this contention on this pin lock. But so even without that, normally your driver should not use any page frag for the headers. It makes no sense. Normal driver should allocate a contiguous piece of memory, DMA coherent, to store all the incoming headers. Let's say you provision up to 256 bytes per header. If you have a ring buffer of 1000 slots, you allocate a single viewed big page of 256 kilobytes. And then on the receive path, normally we just copy the header in the SKB head because the stack will need the header in the SKB head anyway. So it makes no sense to use the page frag to hold the header that will be consumed very soon in a GRO layer anyway. So it makes absolutely no sense. I think IDPF is completely wrong here.
So is any driver out there here that has implemented this? You have? Yeah. How you use your implementation? So Eric, you're saying there is no need for the dual header versus payload pool.
The page pool should be reserved for header splitting concern. If you are doing header split, just use the page pool for the payload, but the header should be split elsewhere, not in the page pool.
There is no need to recycle this stuff. You just go through the normal stuff.
Because, yeah.
Okay, that's one feedback. I thought I was being clever by saying we just use one page for everything, for however many headers, but... Mike over here.
Thank you. Yeah, so we do use page frags still. From a single page pool, although with the devmem stuff, we are moving towards 2 pools, 1 per header, 1 per data, so that's interesting. But I'm not sure I follow. So you have a single large, like a high order page just for the headers?
Yeah.
And you keep it all the time?
Yeah, of course.
So you don't...
It's initialized at ring initialization when you open the NIC, and that's it.
Okay.
And that's a single DMA mapping, by the way.
Right.
So you don't have to play games with IOMMU or whatsoever. Yeah. It's a single mapping, so it's much more efficient anyway.
Okay, that's an interesting idea.
Or another solution is to put inline the headers in the receive descriptor. Some NVIDIA NICs do that.
Yeah, but we don't use that for... Interesting.
You want to add something? David, yeah. Okay. Okay.
And just saying we do things differently.
That's it? That's all you're going to say? Okay. All right, so I'll bring back the original diagram. Okay, sorry, go ahead.
I had one more question if you were checking. So the page pool stats have these like recycle, quick, I don't remember the exact names.
We ended up doing, the IDPF driver does not have page pool stats. Right. So we ended up hooking one ourselves. We're not very experienced. We didn't see anything useful. The data seemed to be, just showing something. There was nothing to read from the data that could reveal anything.
But the contention, so this lock was inside the driver, or was it?
Yeah, so the lock is...
okay, then you would not see it.
So actually, let me just bring up the original diagram that brought up the problem, right? So that brought it to our attention, basically. It's just observing that how do a GRO give us less performance, right? And the real reason is this call called libeth rx_recycle slow. And it basically recycles the dummy, let's say in the example I gave, 15 headers, 15 back to the payload, to the header payload, page pool, I'm sorry.
The page pool already has this mechanism for quick recycling. Is it doing additional recycling? No,
it's just you have to go and grab the producer lock, put back your page. That's the code we saw. And then release the lock. But you're doing one at a time, and there's a cost of grabbing the lock and releasing it. Right? What we did notice with IOURING, for example, is very clever. It's using the cache. Right? So it did not have these kind of issues. And it was not susceptible to this problem. Okay. Now, I don't know if that's by design or just by accident, Pavel. Of course, he's going to say by design, but... Okay, so this is how it works, basically.
Jamal, it's somewhat suspicious that a function that is called _slow over here ends up burning 5% of your CPU.
Yeah, I think, you're right. The suffix or prefix in there, slow, implies that it should not be called that much, right? Whoever wrote the code clearly did not see this. That is not slow if you're recycling 15 pages for every GRO that bubbles up. Okay, so next we run into what I would call the payload recycle dragon, right? So this is another dragon. That one is the header recycle dragon. The other one is the payload recycle dragon, right? So again, the mechanics for recycling payloads from devmem is you call setsock opt. Eventually, we figured out that you could actually batch from user space. You could send as many as, I don't know why the maximum is 1024, but you could send as many as 1024 tokens to the kernel, which will then try to recycle. However, if you look at the recycling thing, it actually also grabs Instead of going into a for loop, instead of grabbing the lock once and then batch recycling, it was grabbing a page, the lock, putting one, releasing, then going back. Now there's a lot of indirection to get to the code that was recycling. So we made two changes because this one looked like an easy fix. So, oh, sorry, someone wants to say something. Yeah.
No, you can finish with the slide first.
You want me to get back to the previous one?
No, I was just going to say what you have on this slide, an identical API exists for page pool to recycle a batch of pages at once.
We ended up using that. We actually wrote our own initially, then somebody noticed that there is this thing called bulk recycle. We hacked it a little bit. It's not, we made some small changes.
Okay, cool.
Yeah, we made, because this is invoked from this signal comes from user space. So it's going down on setSockOpt and then, so it's a different code path. So we had to change. I think we added one more parameter or something like that. I have to go and look.
Yeah, I was just the driver did the same.
Yeah, and if I show you path, you'll see it being called bulk something, right? But we did make that change. It's just where it's being invoked, and I think we added one extra parameter. So in this case, we made instead of the application recycling at every receive, we just collected a bunch of them, and then we would call setSockOpt with a batch of tokens. Now, I have no idea why the kernel insists that it has to be a maximum of 1024. I don't know if anybody knows the reason as to why we can only send 1024 per, what do they call it, per container, right? So that's one, is we fixed our app. So our app now is batch recycling. And then we changed the kernel lock size to basically do the batch recycle. Initially, like I said, we wrote our own, and then we noticed that, is it used in XDP, Talkie? Yeah, it's XDP, yeah? That code is invoked from XDP. I don't know where it's, somewhere from the lower layers, they're invoking the bulk release, I think. Who's the use of that?
There's some drivers use bulk release and some don't.
Okay.
I think MLX5 uses the bulk release and the others should be, I guess.
Okay, so in any case, we grab the producer lock and then that's the loop. You grab it once, you go in a loop, you put back the pages and release the lock. And on average, in our runs with devmem, we saw up to, on average, about 875 tokens coming up on receive message. So that's, if you round that up to 1,000, that's about 4 megabytes at a time when you do receive message, right? So in our change to the app is to, we wait until either we receive 512 or more. If the receive message gives us 875, then we'll recycle the whole 875. There are occasions where we get over 1,000, but we only send, and we will send all of them back as long as it doesn't exceed the maximum number, right? And we did see that the setSockOpt went down. So we ended up adding on statistics in the app, so you can see how many received messages we got. And I can't control my mouse, but yeah, oh, I could, okay. So you can see the number of received messages we got and the number of setSockOpts. The number of setSock are a little higher than receive message, because on average, we're getting more than 512. So we're getting more than 512 per receive message. Our average, so we collected a bunch of stats which gave us a good indication to finally, to tweak again the application, okay? Now, you think that we'll see a good throughput increase, but no. So on the left-hand side is the one CPU, and you can see that, oh, I can control my mouse from here. Great. I need to wake up. Okay, so this is just devmem before the batching, and this is devmem with batching on a single CPU, all right? So you notice that we went from 74 to 92, went 131 to 135. It's not much, but there was an improvement. With the two CPUs, that phenomena is still there. It's that libeth rx slow is still causing us problems, but the numbers did go up. Went from by 10 gig and by another 10 gig. Right, so that's one patch we have. We'll upstream that. Right, it's a small change to your bulk memory thing. Okay, now let's take a look at before and after batching. On the 2 CPUs first, you notice that setsock opt, which used to cost about 43 microseconds, is now costing 27 microseconds. And in fact, the receive message also went down to 94 microseconds from 112. The other ones are pretty much constant. Okay. And if you look at the 1 CPU scenario, it went from the setsock from 205 to 78 microseconds, because we're using this batching, and in the kernel, we're doing a for loop, we're doing a bulk recycle. And receive message went down from 146 to about 114. Okay. So we looked again at perf. There's nothing really else that stands out clearly there. So we'll rely on like black box results to dig any further. So at this point, we're past that map. We're almost close to our destination. So we decided we're not going to test anything on 2 CPUs. To get consistent results, let's just run everything on a single CPU. So we have a single flow, up, and as well as a soft IRQ, they're bound to 1 CPU. Okay. And here's our results. Again, as expected, IOURING performs very well relative to devmem. And we added big TCP. And yes, big TCP does improve things as well. So if you took at IOURING, it went from 183 to 188 with hardware Gero, 136 to 154. Devmem went from 74 gigs with a single CPU to about 88. And on hardware Gero, it went from 131 to 132, not that much, but still an improvement. And slight improvement with baseline. Right, so I guess the summary is do not run just standard socket applications. They're not good, and the system calls will kill you, and they'll also kill you on devmem. But so here we go. We looked at, I'm not as much, the transmitter side is not as exciting. It's doing really well. It's the receive side that's a challenge, right? So if you look at devmem versus IOURING, IOURING tends to be very heavy on soft IRQ execution. Devmem tends to be more heavy on the syscall level, because the page memory management, etc., is happening in user space, right? And if you look at just the sum, so we take the receiver and the sender, and we say, how much total CPU are we using for this one flow, which gives us whatever this throughput is? And yeah, again, devmem and devmem versus IOURING, they're not much different. You notice the difference in the yellow, which is soft IRQ, versus the blue, right? And then you, of course, it's very clear that the blue is killing you on these guys, right? The syscalls, there's no copy, there's a copy here. And you move from this to that with devmem, you're still, in total, the worst case scenarios, we're consuming 2 CPUs, right? We looked at power, very similar behavior on the sender and receiver. The total power being consumed for this one flow is a 680 plus to 700 watts, right? Because you're looking at 2 machines. There's a lot of data there, so we use our famous formula, which we introduced back in Santa Clara, of what we would call the ROI metric. You take the throughput, you use an exponential, let's say, of 2, and you sum up all the CPU that was used. And that gives you the ROI from a CPU utilization perspective. Or you can take the throughput, make n equal to 2, so it's squared. It means I'm really interested in seeing what benefits I guess. And then you multiply the power by a factor, by another exponent. In this case, the exponent was 1. Okay.
So the power here is just the CPU power, or does it also take into account the NIC?
The whole system.
Okay, so it is a platform level thing.
Yeah, we have a box that's sitting outside. Everything goes through that, and it has an API we can invoke. If anybody's interested, bought it online from some Czech company. It's pretty accurate. It's about 99.9 with a single 9 accuracy.
Great, thanks.
Right, so it sums up everything. It's a black box. And the reason we use n equal to 2 is that, let's say you have a 10 gigabit and you consume 200% CPU versus you got 5 gigabits, but you consumed 100% CPU. Which one is better, right? You can't just say the 10 gigabits is better because I got 10 gigabits. It could, if that's what you care about and don't care about CPU or power. Okay. So our metrics next are just looking at the ROI metrics. And again, it's very clear that IOURING is performing very well. Now, like I said before, if I look at the power, you notice the difference is so high for IOURING. That's because there's a little bit of cheating there with the IO weight. But it's still, even without that, it will still, maybe it will end up somewhere here, right? Instead of up there, it will be down here, and this may be down here. But still, IOURING is performing better than devmem, okay? If I look at the sender side as well, we see similar things, like the black means you have a hardware GRO, the blue means you don't have hardware GRO. Same thing with the power, right? And then if you do the total again, there's a huge difference, as you can see. Now, of course, devmem is sitting here. If you do big TCP, you're doing better than without big TCP. I do believe that some of these issues may be bugs that may need to be ironed out. The receive side for devmem looks very stable. The transmit is still shaky, and that's because we took the December version and we patched it with some things. Okay, conclusions. Yeah, these 2.0 copy interfaces, they're all beautiful. At this point, I would say that the disadvantage, of course, is you have to rewrite the application. So there's a lot of people who like backward compatibility. You can just plug in there into your app or write some syscall interceptor and then make it work. You could, but it was not worth it, in my opinion. IOURING, the only one thing I found is, based on discussions, you cannot turn off IOURING for everything else but networking. You either get the whole thing or you get nothing, right? So that is a complaint. Again, the conclusion is devmem is very syscall heavy, mostly because your page recycling happens from user space. While IOURING is very kernel soft IRQ heavy, while IOURING demonstrates a clear advantage, we do not have any link that's above 200 gigs. So maybe if we did 2 flows and try to go 400 gig, maybe we'll see some things that are obviously not observable at 200 gig. Just like we did with 100 gig, there was clearly no throughput advantage for anybody. And now we're seeing there's a throughput advantage if you go above that. The page pool API, I thought that you had to have 2 page pools, one for the header, one for the payload. So that's why my comment there is page pool API could be improved, but it seems like it's a driver choice. The driver decided to do this. And last but not least, hardware GRO presents a big advantage. We did do this payload so there's some backslides when these are published, you'll get, in the backslides you can see a lot more data. But what I wanted to point out is an accelerator. This is an NVIDIA T100. It's one of the, T1000 is one of those things that goes in your laptop probably. It doesn't even have a power connector. It has 4 gigs of RAM, and we did run some dummy CUDA code to just fire it up, because if you don't, it sits at it doesn't fire up the PCI bus. It sits at like PCI 1, X2 or something like that. So you have to write some dummy code that keeps waking it up and then you can see it propping up to PCI 6. And we tested devmem and it worked great. Now, this board is on a Ryzer card, which is X3, PCI 3, X16, so it can do 100 gig with some overhead for PCI payload. It wasn't the greatest, but we were able to do, with hardware GRO, about 85 gig. And without hardware GRO, with devmem, we are doing about 70 gig writing to the GPU memory. Okay? So, yeah, if you run NVTop, if you've done this kind of stuff, you can see, the thing that was, we wanted to get it to run at Gen 3 X16. You can see the bandwidth on the receive side is pretty high. That's probably close to 100 gig right there. So it was consuming 100 gig on PCI, but on the wire it was turning out to be about 80 gigabits. Okay. And so with that, I would like to thank a few people who made this happen in a short time. Anjali, who is not here, I don't know where she is. She's supposed to be online. Was very helpful to us to...
I am.
Oh, there she is. She is, without her, we would not have got Intel to do anything for us, okay? So that's our savior right there. Srida sent us some patches for the driver. Like I said, the RSC is not working. There's quite a few things that are not working that Srida managed through Anjali to give us some patches. Mina, I don't know if Mina is on, but Mina was very patient with us. We went as far as running the GPU orchestrator from Google just to test that the GPU memory. We have some patches to the Nickel plugin, but this is outside of the scope. And Pavel over here, again, is another hero right there. He helped us get any intricacies of bugs that we found in IOURING. He was very responsive almost immediately. So I'd like to thank these people. Without them, I wouldn't be presenting anything in the short term. Now, remember, I was going to do this in a week. Victor and I were, I thought Victor was going to do it in 2 days. Then we had to, we all, because we're just collecting results, right? Just go and run it, and we have everything we need. And like I said, the map was full of dragons and big snakes that we had to cross. But we persevered, and here we are. Thank you. Questions? So I do have some 5 minutes, is it? Do I have 5 minutes? Or 3:56? What time does it end? Okay, there's a question. Yeah.
So if you go back one slide, when you say IOURING is soft IRQ heavy,
Yes.
did you normalize the soft IRQ usage to the bandwidth? Isn't this just because it's achieving higher throughput, and on the other devices, you don't get the soft IRQ because you're not pushing enough packets?
We did not try to separate whether the ROI was how much soft IRQ was being used. We just summed up the syscall plus soft IRQ and used that as what we would normalize with throughput. Right? That's what we call the ROI formula. This formula.
Yeah, yeah. I'm just calling it soft IRQ heavy. Maybe just yeah, you know, it's just it actually achieves the throughput where the kernel has to spend the cycles to process the packets, whereas the others you're spending the time in syscalls, so there's no cycles left over.
You could argue that that's why I say 200 gig is a good start. I can't reach a conclusion 100% that devmem would not work as well, because if, and Pavel, you can correct me if I'm wrong here, but the recycling happens in the same CPU where the page was grabbed from in the page pool, and it's basically on the same software IRQ. So at some point, at a high enough throughput, I think you run out of software IRQ cycles. All right. Am I correct? Mike? Now, again, please look at this as micro benchmarks. I believe both of them can do 800 gig with enough flows and enough queue pairs, right? You can distribute the queues and put 200 gig on 4 queue pairs, and you can probably, or 8 queue pairs, and you can get your 800 gig out of this. I don't know for sure, because I don't have the hardware to prove this or not. I only have one NIC, which has 2 by 100, which can be converted into 200 by 1. Sorry.
I would say the RQ difference is pretty much, the soft RQ difference is pretty much expected because some of the page accounting that devmem does from the syscall pass, IOURING just does in the soft RQ from the page pool. So the overhead just shifts into the page pool. So.
Yeah, the question is the memory management or the page recycling policy used by IOURING, which is done in the kernel at soft RQ, is better than what devmem is using because it's recycling through setsoc-opt, right, from user space. Now, there may be a reason for this application-wise, maybe PyTorch or something that's doing GPU training requires that a lot more control is given to user space. I am not privy to this. Maybe someone else can comment on this.
Yeah, that would be my guess, Jamal. I mean, there's some context awareness of which pages need to be posted back for a C or something when it is the accelerator use case instead of the application. I'm guessing that's one reason. I mean, the other way to look at it, if you were to change the MMTCP to use the page recycling in the kernel, could you make it work for when you're using the MMTCP for an accelerator use case rather than the application? Do you see any reason that wouldn't work?
I don't know if you, I think the design is already saying the recycling has to be done through setsoc-opt. I'm not sure it's a bad design. Like I said, we're limited by the bandwidth we have. The other thing I should mention is IOURING does not have DMA buff, but you're looking to do that, Pavel? Yeah. Can I get it tomorrow? Just kidding. Okay. Yeah, there's...
Just a question about the devmem or the benchmarks. Are you going to share them? Especially on the devmem side, there's not so much benchmark out there.
Yeah, let me... Wait, let's talk. I could give you access.
Thank you.
Right, it's... Are you a Rust programmer?
Sorry?
It's written in Rust.
It's, yeah.
Okay. But we could go over code, for example, and tell you what the architecture looks like. So you could probably write it. We're doing a lot of batching with devmem, right? The design of having the completion queues, the way IOURING is designed with queues, with the rings, I'm sorry, maybe a better alternative. At least at this point, it looks like a much better design, right? Any more questions? Thank you. These slides will be posted and everything online at the netdevconf website. Okay, I managed to pull through this. Thank you.